Okay, and the last technique I want to cover in this section is smoothing splines. And I guess really maybe this should be a section in its own right, because a smoothing spline is not technically a regression spline, it's actually quite a different approach. Unlike regression splines and natural splines, smoothing splines do not require manual knot selection, so we're not going to require knots at all. The basic principle is as follows of smoothing splines. In fitting a smooth curve to a set of data, we want a function gx, this is our smooth function, that fits the observed data well. In other words, we want the residual sum of squares of the difference between the actual value of y and the function of y squared to be small. Now, without putting any constraints on the function that we estimate, the residual sum of squares is going to be smallest, that is 0, when this function is chosen so that it interpolates all of the y. In other words, it just essentially turns all of the x into a prediction of y, and of course, provides a very good fit, but it's very, very squiggly and it's just overfitting the data. It's not really finding a trend in the data, it's overfitting to noise in the data. And we saw that actually in the diagram we had previously. Yeah, so that's an example of where it starts to overfit the data. It starts to interpolate the y's too closely. Ultimately what we could end up doing is just join the dots, and that would give us a perfect interpolation, and that's what would happen if we were to put no constraints on this function. We would just join all of the dots. So the principle underpinning smoothing splines is to find a reasonable function, a function g that makes residual sum of squares small, while simultaneously ensuring that we've got a reasonable degree of smoothness, so it's not too wiggly. We're going to penalise wiggliness. And a natural approach to achieve this is actually to minimise this form of residual sum of squares. So we have the normal residual sum of squares here as the first term, but then we have a second term that is essentially a penalty for overfitting the data, a penalty for things becoming too wiggly. This parameter here we've got called lambda is referred to as the tuning or smoothing parameter. It's non-negative. And the function that minimises the above criterion is known as a smoothing spline. Now, importantly, note that the above criterion takes a particular format. It's got a format of a loss and a penalty. The first term is the loss function. That's measuring how well our function g fits the data in the usual way. The second term, lambda times the integral of the second derivative squared, penalises curvature in the function. It does this since the second derivative, which essentially measures curvature, will be larger in absolute value if the function g of t is very wiggly near t, and it will be close to 0 otherwise. So this penalty term then is therefore a measure of the total change in the first derivative of the function g over its entire range. The larger this term is, the more nonlinear the function g is. And that's what we're going to try and penalise, and we're doing it through this parameter lambda, the tuning parameter, that establishes, essentially there to establish a trade-off between loss and penalty. So in the above minimisation criteria then, this term here encourages the function to be smooth, and the tuning parameter modulates that smooth. The smaller the tuning parameter, the more wiggly the function, eventually incorporating y when lambda equals 0, because of course then this term just disappears. And as lambda approaches infinity, the function becomes less wiggly. Essentially approaching, as it approaches infinity, it would become linear. So in that sense, we can say that lambda is controlling the bias variance trade-off of the smoothing spline. That's essentially what it's doing. Now it can be shown that the function that minimises the above criterion has two special properties, and we're not going to derive this formally because it's quite mathematically involved, and we don't need to. It's not what we're interested in here. But the function that minimises the above criterion has two special properties. First, it's piecewise cubic polynomial with knots at the unique values of each value of x, and it has continuous first and second derivatives at each knot, and it's linear in the region outside of the extreme knots. Notice that, outside of the extreme knots. So equivalently, we could say that actually G is a natural cubic spline, linear at the outer intervals, but a cubic polynomial piecewise, with knots at each value of x. However, it's not actually the same as a natural cubic spline obtained using the basis function approach described previous to those knots. It's a shrunken version of such a natural cubic spline, because the tuning parameter lambda is going to control the level of shrinkage. So that's what smoothing splines do. They don't define knots in the way that we've done previously, either manually or by using some uniform pattern of knots. The smoothing spline turns the discrete problem of selecting knots into a continuous problem of penalization, where lambda is going to be the parameter that determines the trade-off. Okay, I've got a slide here that describes how we would calculate degrees of freedom for smoothing splines. I don't think this is desperately important. I just want to say that although a smoothing spline n has n parameters and hence n nominal degrees of freedom, these parameters are heavily constrained or shrunk down by the tuning parameter. So in the context of smoothing splines, we talk about effective degrees of freedom as a measure of the flexibility of the spline. The higher it is, the more flexible, and the lower the bias, but higher variance. So if we think about the solution for a particular choice of lambda, this gives us our solution of the functions that are going to determine our spline. We can write that as a linear combination of the y's, where S is an n by n matrix, and the effective degrees of freedom is defined to be the sum of the diagonal elements of that matrix. But again, it's more of a detail than something that I really need you to focus on. What we do need to consider now is how are we going to choose the tuning parameter? How is that going to work? Because that's what's important here. It's going to determine the trade-off between wiggliness and the loss function, or the trade-off between what we're calling bias. So how faithfully does the curve fit the data relative to the variance of the function? How variable is it across the fit? So we need to think about how we choose the tuning parameter. Now, in fitting a smoothing spline, we don't need to select the number of location of knots. There's going to be a knot at each training observation. What we're going to do is choose the value of lambda that's going to shrink those parameters down, that's going to penalize. Now, one possible solution to this problem is cross-validation, which we talked about previously. If you go back to that slide, that will explain what it is. But what we want to do here is find the value of lambda that makes the cross-validated residual sum of squares as small as possible. For smoothing splines, the way this is done is through what's called leave one out cross-validation error. And it's described on this slide here, this particular form of cross-validation, and you can read that in your own time. But what we're going to do is we're going to find the value of lambda that minimizes the leave one out cross-validation error. And this can be computed very simply using this formula. So you see this formula here. All this formula does is it sums the difference between y and the fitted value of y. But this notation here indicates that this is a fitted value for the smoothing spline evaluated at xi, where the fit uses all of the training observations except for some ith observations. And we repeat that n times, and we sum all of the errors over n trials, and then we simply want to find the value of lambda that minimizes that residual sum of squares. So that's in practice how we can find a value of lambda that is in some sense optimal. Okay, there's many different types of smoothing splines. There's one I want to mention before we close off this section of the lecture, and that is what's called penalized spline regression, penalized splines. They're a very popular type of smoothing spline that can provide a solution to penalty fitting within a mixed model framework, and that's really why I want to talk about it, because it connects to the mixed models that we've discussed in a previous lecture. So to appreciate the concept, we're going to consider a general spline regression model. You know, we've seen this form before, with k-knots where k is large, and this is of degree d. We could write the ordinary least squares for this model in this form here. We're going to minimize the usual expression, and that's going to give us our parameter vector. But unconstrained estimation of beta might lead to a wiggly fit, because we've got very high D and we've got a very large number of K. To rectify this problem, we want to use a loss plus penalty format. So we're going to keep the basis dimension fixed at a large size, but we're going to control its smoothness. Now, since the function g of the smoothing criteria, written in this form here, is linear in the parameters, this function, which we plug into the smoothing criteria, is linear in parameters. The penalty, it turns out, can be written in quadratic form in beta, in this form here, where D is a matrix of known coefficients. And again, the detail of this isn't hugely important. Minimizing that expression subject to the condition that, subject to this condition here, that this reaches some particular value, is equivalent to choosing D to minimize that expression there. Sorry, that D shouldn't be there. For some number lambda, which is the loss penalty criterion of the smoothing splines that we lost before. So in other words, we can derive lambda by making this minimization problem. And importantly, actually, and this is really the main point I want to make in this part of the lecture, this can be achieved very simply by Remel estimation of the mixed model. So if we write our mixed model in this form here, where Z contains the spline basis functions and the random coefficients U, assume normally distributed with variance sigma squared U, sigma squared U actually is equal to the variance of the error term divided by lambda. So a mixed model framework can give us a direct estimate of the penalty term. So for example, the design matrix here, if it was just, if we just had 1 and X in the X design matrix and knots K1 to K to kappa K, would give n rows in Z of Xi minus K1. This is just a linear spline. Then that's the solution that we would be getting. Now, the problem with this format, the reason why I haven't written it out in general, is because it depends on the degree of the spline and the number of constraints. All I really want to tell you is that assuming a normal distribution and treating U as a set of random coefficients, variance components, then the best linear unbiased predictor of the linear mist model can give us a solution to the penalized spline fitting criterion, where lambda falls out of the process of estimating the variance components. And this slide here just shows the minimization problem solution. The amount of smoothing is controlled by lambda, and these are the fitted values. So penalized estimation then, last point, shrinks all coefficients of spline basis functions towards 0 and can be contrasted with knot selection, which shrinks some coefficients to 0 while remaining coefficients are unshrunk. Okay, let's just look finally at an example of smoothing splines for the open air data. We're going to first fit a smoothing spline and use cross-validation to choose the tuning parameters. So that's automatically chosen via cross-validation, sort of optimal in a sense. And then we're going to fit a smoothing spline with pre-specified effective degrees of freedom. And we're going to specify the degrees of freedom to be 10. And that's going to fit uniform knots on the curve. And we're going to plot the data in the usual way. And this is the plot we get, the estimated smoothing spline. So in this diagram here, the red curve indicates the fit obtained from pre-specifying the effective degrees of freedom as 10, and it gives us a nice smooth curve. The blue curve is the smoothing spline obtained when lambda is chosen using leave one out cross-validation, which results in a higher amount of degrees of freedom, 28.8. And you can see what that does. It makes the curve wigglier. Okay, so it's not as smooth. It's smooth, but it's not. It's more non-linear than the curve we get with just 10 degrees of freedom. And although that curve, the blue curve, the one that's fitted by choosing lambda automatically or optimally, let's say, using leave one out cross-validation, although that's wigglier, That may well be the case. That may well be showing us things that are important. In other words, the former simpler curve, the red curve, might not be capturing some of the non-linearities in the data that are actually of potential interest.